All right. Hello, everybody. Again, to everybody who's here, and for the first time to everybody who's watching later. This is a meeting of the Philosophy Club at Sacramento State. Currently still unofficial, but let's see what happens next year. My name is William Wyatt, and today we have a talk by Professor of Philosophy at Sacramento State, Manuel Barrantes, on the ins and outs of simulation explanation. So without further ado, let's give the mic over to Professor Barrantes.
All right. Hello, everyone. So, give me. Okay. So, if you have questions about my talk, please interrupt me right away, and I can stop and clarify. This is actually a work that is very, 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 very in its initial stages. So I'm trying to put together a view that relates my work in philosophy of mathematics and the works of one colleague that works on the philosophy of computer simulations. And we saw that there are some similarities and differences between our fields, and we're trying to put together a paper. And this is the first run that this paper has ever had. But I have to be honest that I just finished putting up the PowerPoint 10 minutes ago. So this is very work in progress, and I am very welcome to, I'm perfectly fine clarifying some things. I am also aware that philosophy of mathematics is not something that you have received throughout your education in great quantities. So if you need clarification on anything, please let me know. And with that, let's go. Wait, okay. So the goal of this paper is to, and William, I should talk for 30, 40 minutes?
However long is sort of natural. I try to go for around an hour per meeting, but I don't like cut things off,
Okay, perfect. All right. So the goal is to compare mathematical explanations of physical phenomena with simulation explanations of physical phenomena. And the background that you need is a distinction between internal and external explanations, and I'm going to provide that background. And the two theses that I will defend is that in mathematical explanations of physical phenomena, internal explanations are not a necessary component of external explanations, but in simulation explanations of physical phenomena, internal explanations are a necessary component of external explanations. What am I talking about? Probably you have no idea, but the goal is to clarify all this, right? Okay. The central argument is this. Mathematical explanations of physical phenomena use models that are optimal representations of the phenomenon that they want to explain, but simulation explanations use models that are different. They are constructed by processes that require many adaptations and adjustments. These are the simulation models. So this is one difference between the two. Given that optimal representations provide transparency in the way that they represent their target, this facilitates the physical interpretation of the results of the calculation process. But on the other hand, simulation models carry opacity regarding the operations carried out by the computer when the simulation is run. Because of this opacity, unlike the case of mathematical explanations, you do need an internal explanations of the simulated results in order to have a genuine simulation explanation of a real phenomenon. Basically, when you have a mathematical explanation of a physical phenomenon, the model is obviously the right one, and then you do your math in the model, and the result, it's very easy to interpret back into the target system. Whereas in the case of simulation explanations, when you run the simulation, the model that you're using is very opaque, and you don't really know what's going on. And oftentimes you get results that are weird. So in order to just simply translate those results back into the world, you need to explain them. You need to understand why those results obtain, which is tricky because the simulation is provides epistemic opacity, but that's a previous step that you have to carry out in order to sort out which results are applicable and which results are not. Okay, so the plan is to talk about the application of mathematics in science in general, and then specifically talk about mathematical explanations of physical phenomena, make a distinction between internal and external mathematical explanations, and then use this framework to understand how explanations by computer simulations work. So in other words, I'm gonna be talking about 3 different areas of the philosophy of science: applicability of mathematics in science in general, specifically mathematical explanations of physical phenomena, and then explanation by computer simulation. These are the 3 fields that my talk covers. If you leave this talk with understanding of either of the 3, then it's a worthy goal. I understand that the whole trio, it's a little bit difficult. All right, so let's get started. Let's talk about the application of mathematics in science in general. This is the inferential conception of the applicability of mathematics, advanced by Ottavio Bueno and Mark Collivan. Basically, what they say is that you have an empirical setup, and then you represent that setup with a mathematical structure. And when I move the arrow, do you see the arrow that I'm moving? So I can use it as a pointer.
Yeah, we can. I can see
Yeah.
the pointer at least.
All right. Awesome. Okay. All right. So so you have an empirical situation. You represent it mathematically. Then you do some stuff at the mathematical level, and whatever you get here, you interpret back into the empirical setup. That's the inferential conception. Bueno and Collivan, it has more than 10 years. It's based on other similar notions, and is very straightforward and accepted. Here's an example. You have a gas tank that explodes, and you know that it exploded because the gas temperature increased, and that increased the pressure. So you use math to have a better understanding of the situation, and it would be something like this, right? You have the actual atomic molecular energy of the water, then you model this with a mathematical representation, right? So you measure the average kinetic energy, and then you put a number to that, right? And the outcome of that measurement process is a mathematical object, right? And then you use this nice mathematical equation here, and you deduce that the pressure is going to be such and such, which is higher than the limit that the gas container can resist. And you interpret this back, and that's how you explain the explosion, right? So you have the empirical phenomenon, you model it mathematically, you do your mathematical thing here, and then you go back. That's pretty much it. That's how you use mathematics in science. Mathematical explanations of physical phenomena are a special case of these standard interpretations of applications of mathematics in science. Here's one of the most famous examples. Oh, first, basically, mathematical explanations of physical phenomena work like this. The same, you have a representation of the empirical setup, then you carry out a derivation, and then you interpret your results back into the physical world. The trick of these mathematical explanations of physical phenomena is that the representation is something that I call optimal representation. It's a kind of mathematical representation that is weird. It captures absolutely everything about the target system that you wanted to capture, right? So for example, when you measure the energy of the water molecules, it's always an approximation, right? You're never going to get exactly all the information that you need. And if you had more physical information, your representation would be better and your explanation would be better, right? But these mathematical explanations of physical phenomena are weird cases where the empirical situation is such that you can model everything that you need to the explanation. It's kind of like an optimal model. It's a perfect model. It has everything and only what you need. Okay. Here's one of the famous cases. This is, imagine that this is the actual system of bridges in the city of Königsberg 250 years ago or more. They were arranged like this, and people they saw the physical bridges and the islands and the land masses, and there were like 7 bridges, and they were physically trying to stroll around the city, covering each bridge only once, right? So they were trying, they couldn't do it. And eventually somebody showed Leonard Euler that it's not an accident that they couldn't do it. It's actually impossible to do, right? But then again, how many bridges? 7 bridges, that's less than 200 possible routes, I think. So in this particular case, methodic Königsbergian could have systematically worked over every single part of the city and then try all the routes and verify that none of them satisfies the requirement and shown that the trip is impossible. But the question is, why is it impossible, right? Verifying that is impossible is one thing, but understanding why is a different thing. And the explanation for why also came in the hands of Leonard Euler, a famous mathematician. He modeled this empirical setup using this mathematical representation, which comes from graph theory. Actually, this is probably the first instance of graph theory ever used. And then he, figured out a theorem, which is, and now this is called an Eulerian walk, a walk that covers all the edges, without retracing your steps here, covering all these edges without retracing your steps. That's an Eulerian walk. And in this case, it's impossible. And the reason why this is impossible is because in order for that walk to be possible, the system has to have either 0 or 2 nodes or pieces of land here, right? But the system has to have 0 or 2 odd pieces of land. I forgot to write odd here. 2 odd pieces of land, right? So he discovered this theorem where you show that, if you only have 0 or 2, then the walk is going to be possible. But here you have this node with 3, so that's odd, another one with 3, and then another one with 3, another one with 5. So it actually has 4 odd nodes. Therefore, the Eulerian walk is impossible in this case. And that's the explanation. And what you can see here, I'm going fast here because this is part of the general point, but not crucial. You have an empirical system, you have an optimal representation. Why is this optimal? Well, because once you represent every bridge as an edge and every landmass as a node, there is absolutely nothing else that you need from the situation in your mathematical representation. Doesn't matter the material composition of the bridges, doesn't matter the size of the length of the bridges or the areas of the land masses, the angles in which this is arranged. It really doesn't matter. The only things that you need are number of connections, number of nodes. That's all you need. And once you have this model optimally represents the system with respect to the problem at hand, which is whether or not such a walk is possible, right? And then you have this theorem, and by applying the theorem, you realize that an Eulerian path is not available in the graph, and then you interpret this back, and that's how you get that it's impossible to walk over all the bridges, right? So this is a perfect example of a mathematical explanation, which is perfectly understood under the inferential conception, right? An empirical setup, mathematical representation, you do your math here, and then you interpret this back. The difference is very subtle. It's simply that in this case, it's not any mathematical representation, it's an optimal representation, one that captures everything that you do. And one question here that has, people have been talking about this for a while now, and one question that arises in this context is whether or not we actually need to know Euler's proof of this theorem. Remember the theorem that I cited here? The question is whether or not, in order to have a full understanding of the impossibility of performing the walk, we do need an explanation of this mathematical theorem. Do we need to put an extra layer of, the actual mathematical proof of this theorem, right? So that's a crucial question that people are asking here. And this leads us to this issue of internal and external mathematical explanation, right? So do we need an explanation of Euler's formula? Right. Here, basically what we have is this. An external explanation would be if you take this as the mathematical explanation and this as the phenomenon that you want to explain, the question is whether or not once you represent P with this M, P is the physical system, once you represent it with the M, you need to provide a mathematical explanation of this M, right? Whether this arrow, it's a mathematical explanation, M prime of M, right? Whether the proof of the Euler's theorem has to be an explanatory mathematical proof, strictly mathematical proof. And I have argued in another paper that this arrow here doesn't have to be a mathematical explanation per se. One simply needs to be sure that you're tracking down empirical structures throughout, just like in other cases of mathematical applications, right? When you apply the formula that relates pressure and volume, etc., you are manipulating variables, but you have to keep in mind that those variables stand for real things that are happening in the empirical world. The same here, right? We're using an Eulerian, we're using a graph, but you should always keep in mind that the graph is representing the actual bridges and the actual connection. So whether or not the derivations that you do at the mathematical level qualify as explanatory proofs within mathematics, that's an issue that philosophers of mathematics should worry about. We are not worried about mathematics per se. We are worried about the empirical structures that we are representing by the math, right? So the question here, do we need an explanation of this theorem? The answer is no. And the reason is that in principle, it's hard, but in principle, you could have, I don't know, counted the number of bridges that connect each piece of land. And then once you get here, it all depends really on the definition of a bridge, right? So you're representing this edge is actually standing for a real bridge. And arguably, had you looked very hard at the connections, you could have proven that the walk is impossible without math, just by looking at the bridges. So there's a sense in which mathematics is not indispensable for this explanation. It's a very helpful tool, but it's not indispensable, right? So the conclusion of this side is that when we have a mathematical explanation of a physical phenomenon, I call it an external explanation because you are explaining something external to mathematics. And the crucial thing is that whatever you do at the mathematical level doesn't have to be an internal mathematical explanation per se. It only needs to be any kind of derivation that tracks down the real empirical structures. Okay, so now with this framework, let's talk about simulation explanation. Alejandra, ándate para allá con la mamá. De ahí vienes, de ahí vienes. All right. So that's,
pardon,
yeah.
Could
I
we
feel like
spend just another moment here? So
yeah, go ahead.
I wanna make sure that I'm clear, and forgive me if I'm just like missed something, but on the difference between external and internal explanations in mathematics.
Nice. Okay.
Because maybe I think what I'm catching on is like external to mathematics, or is it, or are we characterizing this an external explanation as something external to the phenomenon being explained?
Oh, nice.
Is
nice.
maybe where
Okay.
I'm coming from.
Nice. All right. So yes, that I should have clarified that. That's a good point. External to math. Yeah.
Also,
so
we have a question from Justin, which I think may be covered, but I do want to give it the air.
Oh wait, I didn't see the thing in the chat. Let me answer you first, and then we'll go to Justin's question. So yes, the idea is that in order to use math to explain something external, you need to do something internally with the math. And that internal thing that you do with the math, the question is whether that thing that you do has to qualify as an explanation, right? An explanation of a mathematical fact, right? And my answer is that no, it doesn't. Whether or not, because there are tons of different criteria, and there's a huge discussion in the philosophy of mathematics about what counts as a genuine explanatory proof, as a genuine mathematical explanation of mathematical facts. And there's tons of requirements. And my point is that scientists that use math, even in cases of optimal representations, they don't care about the debate in the philosophy of mathematics. They absolutely don't care about it. They only care that whatever they do at the mathematical level is tracking down empirical structures. So that's my main point. Yeah, and there was another question. Is that
maybe. So I think this regards the point on being able to sort of look at the system of bridges and islands and being and without mathematical proof,
yeah,
being able to kind of figure out and even conclude that
yeah,
it is impossible to do the Eulerian walk.
yeah.
Because and this is from Justin, because there is an odd number of bridges to the middle island. Would that I don't think that tracks the exact theorem that
Well,
we discussed. I think that the questions before that was presented, but like, is that close to
I mean,
your
it's
explanation?
yeah, because the really, when you look at a bridge connects two pieces of land. And of course, I know I'm using number two when I define bridge, right? But that use of number two is innocent. I can paraphrase that in first order logic with identity without using mathematics. Like, so in other words, I can express that two without math. And then in principle, I can carry out all this without math. And of course, in principle doesn't mean that in practice scientists do it, right? In practice, scientists use math because that's a shortcut, right? But in terms of the quality of the mathematical derivation, the reason why scientists don't care whether or not what they're doing qualifies as a mathematical proof is because they are not thinking about mathematics. They are thinking about the empirical structures represented by the mathematics, right?
Yeah.
So once you show that it's in principle possible, then you're good to go, right? In practice, might not be.
Yeah. So on the internal external thing, and this might become clearer as we go on. So I don't want to spend too much time on it. But what would be an example of a strictly internal explanation? Just because
Yeah, yeah.
maybe I'm the only one missing anything here. But like,
No. I mean, I don't want this to. I didn't want the talk to really get into all the details of the philosophy of mathematics thing here. So first, my answer within the talk is simply that whatever it is, it doesn't matter, right? That's the main point here. Now, what would be an example? For example, a proof by induction. It's an explanatory, according to some people, that's an explanatory proof because it not only shows that the result obtains, it also gives you an insight as to why it obtains, right? Other proofs by brute computation, they show that, but not why. So there's some debate there as to, for example, if I want to, if I want to prove that the product of three numbers, natural numbers that are in sequence, is always going to be an even number, well, then I can work on the fact that a string of three numbers, there's always going to be one that is even a string, a pair of two numbers that are consecutive, that product is always going to be even. So again, you can work on the details of why the product of an even number by any other number is even, right? So that's going to give you insight as to why the theorem obtains, and not simply a verification that it obtains, right? But again, when you get, there are many trick cases where some obvious general conditions are not met. And so there's a huge debate as to what is exactly the right definition of an explanatory proof in mathematics, right? The point is that that debate is not relevant here. It's relevant insofar it is not. You see what I'm saying?
Okay. Yeah. So like, I like that what we're working towards here is like, the question for like when we're talking about computer simulations isn't whether and to what extent those explanations are like internal or external to what we're looking at, or even whether they're strictly necessary to be as explanatory frameworks, but just whether they like give insight into why, you know.
So let me get into section 4 and we talk about simulations. But for now, the main point is that mathematical explanations of physical phenomena are not essentially different from ordinary applications of mathematics in science. The only difference is that you have optimal representations, but in terms of the operations that you do at the mathematical level, it doesn't matter the quality of those operations as long as they track down empirical structure. So that's the main thing, right? So in the technical language that I just introduced, an internal mathematical explanation is not essential for an external application of mathematics, not even in cases of mathematical explanation. Right now we get to computer simulations, and we have this model by Octavio Bueno, 2014. According to Bueno, the empirical setup in simulations is, this is one view, right? The view by Octavio Bueno. This is the way the inferential conception would be applied to the case of explanations like computer simulation. And do not be misled by me putting this diagram here, because some people argue that the inferential conception that I showed, in the first part, and that I applied to mathematical explanations, also applies to explanations like computer simulation. But I don't think that's true, right? So that's going to be the main point. The inferential conception, if applied to computer simulations, would work as something like this. You have an empirical setup, then you represent it with mathematics, that's the model, and then you implement those mathematics in the simulation, and the simulation is kind of like a huge calculator that you use to carry out mathematical operations that are super complicated, and then those results go back here, right? You read the computer, and the computer tells you that the answer is 4, and then you now know what's the answer to this mathematical problem that you had, and then you put it back into the empirical world. And that's how, according to some people, computer simulations work. They are simply calculational devices, right? So that's the use of computers in science. Is you have the empirical setup, you model it with math, but your mathematical representation is crazy complicated, so you need to implement this into a computer, and the computer helps you solve it, and then you put it back, and everything is nice and clean. So this would be an application of the inferential conception. But I disagree. And my disagreement is based on one collaborator that I have. We're working together on this paper, and he's the kind of like the expert on the computer simulation side. And basically, the disagreement is that the simulation is not just an implementation of a mathematical model. The simulation is much, much, much more. So it's not just a matter of bringing in the simulation in order to crack some mathematical operation that you can't because you are human and you're dumb, right? And you need the computer. It's not just that. When you implement the mathematical model in the simulation, you are doing way more than simply, inserting numbers in a computer, right? So this model I will reject. That view, the view that as a computer simulation is simply, an implementation of mathematics, it's called the calculational view of computer simulation. And it's endorsed by, here are 3 examples that I'm going to read. Paul Humphreys, my PhD advisor, he says a computer simulation is any computer implemented method for exploring the properties of mathematical models where analytic methods are unavailable. That's straightforwardly what I just mentioned, right? Humphreys changed his mind several years after this, but this was his first take. Rich also says a simulation uses a dynamic model of a natural system that produces the phenomenon. It uses the model to imitate the natural system production of the phenomenon. So they are pretty much crunching the numbers in your dynamic model, which is a mathematical model, right? And Otavio Bueno, my other PhD advisor, which I also disagree with him here, he says, I offer an inferential conception of computer simulations, emphasizing the role that simulations play as inferential devices that represent empirical phenomena. So again, the idea is that if your math represents the physical world and you simply implement the math into the computer simulation and you use the computer to carry out operations, then of course the role that the computer is playing is a purely representational, right? Okay, so here's an example that I will use. The example is not new. What is new about this paper is the comparison between mathematical explanations and simulation explanation, right? So in other words, I'm trying to be like very clear on what's the scope of the project. I have worked on mathematical explanations a lot, establishing all the theses that I just mentioned. And Juan Duran, my colleague, has worked on computer simulation and explanation, establishing the thesis. And this paper, we're trying to compare the two. So this is an example by Juan Duran, right? Again, so this is just a satellite orbiting a planet. And of course, because of the gravitational attraction, the moon is gonna drag the water at the surface of the earth, right, towards it when it's at this position. And that mass of water will also retroactively interfere in the orbit of the moon. So the orbit of the moon is not going to be like perfectly elliptical. It's going to have some movement, right? Because the water is so much that the water drags, the moon drags the water drags the moon. There's like a weird, complicated thing. The mathematics to calculating that gets super, super, super complicated. And that's why scientists model this with a computer simulation. First, they throw a relatively standard mathematical model of what's going on here, right? And they try to implement this into a computer, right? And this is a visual representation of the simulation. The visual representation is not the simulation in itself, although it also conveys information about it, right? But it's a visual representation of what's going on in the computer. Okay. Now, once you do this, here is what you find. The results of the simulation are weird. What you're measuring here is the eccentricity, and perhaps I should have introduced this concept, but if you have a parabol, the eccentricity is the distance between the center and one of the axes, right? So it determines, that a parabol is not a perfect circle. It's kind of like an oval, right? The eccentricity measures how oval is your circle, your ellipsis, if you want, right? Is it like this or is it like this? The eccentricity measures that. The crucial thing here is that once you measure the eccentricity of the orbit, it has some spikes, right? It gets like, it's like the satellite gets, it becomes a strain, right? But the weird thing is that when they ran the simulation, they realized that there were these spikes in the eccentricity of the ellipsis, but there was a downward trend that in the end was going to collapse into zero. So the eccentricity was going to be zero, which means that the orbit, according to this simulation, would have collapsed into a perfect circle. But that's not true. We know that that's not true. The orbit, it continues to be elliptical, right? But the simulation threw these results. If running simulations was just a matter of getting your results and interpret them back, then anyone who doesn't know anything about astronomy would be like, oh, you know, after a while, all the satellite orbits become perfectly circular, which is not true, right? So there's something wrong with these results, and there's something right with these results. What is right is the spikes, right? That represent the fact that, you know, there's kind of like a strain going on there, right? Here's the thing, and this is the crucial part. We have the spike, and we have the downward trend of the eccentricity of the ellipses. If simulation was just a matter of crunching your mathematics with the computer, if the computer was simply an instrument, then there wouldn't be a way of explaining what's going on here. But it seems, and that's the thesis that we're putting forward, it seems that whenever you use a computer simulation, if you want to use the computer simulation to explain an empirical phenomenon, you first need to explain the results. The results are a unit of analysis in and of themselves. So much so that whether or not you then use those results to explain an empirical phenomenon is really irrelevant. I mean, of course, if your goal was all along to explain an empirical phenomenon, then of course, you know, once you explain the results, you use that to explain the physical phenomenon. But there is an interesting thing in and of itself in explaining the results of the simulation. They are a unit of analysis in themselves. So that's the main point here, right? So here's the key claim. The simulation model is what you actually implement in the computer. You don't implement in the computer the mathematical model. You implement in the computer the simulation model. And the simulation model, it's a product of many non-mathematical considerations that you need to make in order to make the initial mathematical model amenable to algorithmic processing. For example, here you model the, first you need to implement some mathematical distortions, right? And break down the mathematical model that is perfectly linear into, you know, some discrete steps, because the computer works as discrete steps. The computer doesn't have a mind that makes mathematical calculations, right? It's a mechanical object, right? So you need to introduce simplification, discretization, distortion, removing degrees of freedom. And also the computer itself, it's a mathematical object that gets hot, that has, you know, radiation from, you know, solar neutrinos. It's a mathematical system, right? So it doesn't, the computer doesn't look into the Platonic mathematical heaven, right? I mean, we don't do that either, but there's definitely something about mathematical intuitions and understanding of continuous functions that the computer doesn't have, right? It's a machine. So once you get all this in place, what you get is a simulation model. That's what you put into the computer, right? So this brings us to the explanatory view of computer simulation. Computer simulations are not simply devices to cracking down mathematical equations. They produce results that are amenable to explanation in their own right, right? So in explanation by computer simulations, the results of the simulation must be explained prior to any empirical application. That's the main point, right? So in the particular case that we are discussing, the eccentricity decreases, but this is due to a rounding error, right? So you need to see what is it that happened when you were implementing the simulation model, right? And that's going to give you understanding of those particular results. It's not about math anymore, right? There was a rounding error. There was like a concrete problem that was introduced, and you need to understand why the results occurred prior to an application. Whereas the spikes are due to actual tidal stress. So you can interpret easily the spikes in terms of the target. But in order for you to distinguish between the two different results, you need to introduce an intra-simulation explanation first. And the simulation explanation is it occurs once you use the simulation model to explain the result, right? Because you need an understanding of what's going on there. All right, so this is a simple example, but I think it clearly illustrates that whereas in the case of mathematical explanations, a mathematical proof is not necessary, here in the case of simulation explanation, a simulation proof of the results is necessary because you need that understanding in order to know what works and what doesn't work, right? It doesn't happen in the case of mathematical explanations because you have a model that is perfectly transparent. Whereas here, the interpretation is never straightforward because it's impossible to track down what is really going on in the algorithmic processing of the computer, right? So that makes things even more complicated, right? So the question, do we need to add an explanation of the simulation results? And the answer is yes, otherwise you wouldn't understand the results obtained, and that's a crucial step for applying them to the physical world because you always have this possibility that extraneous results will crop in. Okay, so basically my conclusion is this. I have used an analysis of mathematical explanations of physical phenomena to highlight important aspects of simulation explanations of physical phenomena. In particular, I have argued for two claims. There is a distinction between intra and extra explanation, both in mathematical explanations and in simulation explanations of physical phenomena, right? And intra explanations are necessary for simulation explanations, but not for mathematical explanations. And that's all I have. Thank you so much.
No, thank you. Jeebus. Perhaps it's only because it's all relatively new to me whereas my concentration is on ethics and politics and whatnot. But I'm enthralled by this.
Okay. William, can I say something before? Yeah. All right. So let me repeat what I said at the beginning, and I can wear my philosopher giving a talk hat and my professor talking to students hat. Right. This is a mix, or I can use it as a mix. I don't know. It depends on you. But my point is that I have talked about an issue about mathematics applications in science, straightforward cases like the temperature case and the tank blowing. I also talked about the Königsberg case as a special case of those where you really have what appears to be a mathematical explanation of a physical phenomenon, but it's not really, right? So that's another area that is also interesting, and there are many ontological questions about the existence of numbers associated with that discussion. And then there is a third point about computer simulations, and that's the tidal stress on the satellite. So we have the gas container exploding, the Königsberg bridges, and the satellite simulation. And don't feel that you need to ask a question that tracks down everything, right? So you can use you can focus on a small portion and at any point and ask me about that, right? So don't need to have like a full coherent picture of everything.
Yeah, and I certainly don't. One of the things that I'm liking about this and that I'm kind of taking away from it and I want to run it by you to check is that one of the sort of normative consequences maybe of the explanation model of computer simulations is that essentially we cannot rely on computer simulations, however sophisticated, to kind of do all of our thinking for us. So contra the somewhat pessimistic, somewhat optimistic predictions for artificial intelligence way out in the future that it will kind of understand the world so much better than we do on an order of magnitude, such that it's like an existential threat,
nice,
or something along those lines. There's a the fallout basically from what we can understand about computer simulations is however complicated they become, there's some things about the world that they can grasp that we can't, and that we can grasp that they can't, or some and that's some secret third thing that could grasp that neither party can't, etc. and so forth. And I'm liking that, partly because it makes me even more annoyed at the book Origin by Michael Crichton, but also possibly because it makes me a little bit more optimistic about how we can and should treat computer simulations and artificial intelligences and so forth in the future.
Yeah, I mean I think that's an interesting point. The fact that there is a strong sense in which computer simulations and computer processing in general is epistemically opaque to us, right? And that has two things, right? You can take actually two opposite conclusions from there, right? So there's nothing that is straightforward, but one is, yes, the results that you get from a simulation may not correspond to the actual physical system that you were modeling in the first place, because something might have happened inside the computer that you are not aware of. So that's one thing, and that kind of like gives some priority to humans in the process of knowing the world using computers, right? There's some humans remain kind of like at the epistemic center. But you can also get the opposite conclusion, because arguably a computer can categorize things in ways that you don't understand because you don't understand those categories, right? So the computer may be able to carve down nature at joints that you can't even possibly imagine, right? So there is a strong sense in which, in this case, yes, obviously the the orbit is not circular, right? So the computer is wrong, right? But there's definitely open the possibility that the computer might be able to categorize things in categories that are not easily to understand for us, which may lead to the unwanted conclusion that humans might not be at the center of the epistemic enterprise, right? So what I'm saying is that the conclusion that you make from here, it's it's a very good one, and I think it's perfectly acceptable. But somebody might use this notion of epistemic opacity in the opposite direction, and in a relatively sound way as well, right? So there's room for debate there.
Yeah, absolutely. And I'm just going to state something clerical for those who are here.
But
I'm going to continue to talk for just for a few more minutes probably, but again, if anybody
yeah,
who raises a hand gets the floor, that's the rule for me. And
that's right. So yeah, so is there anyone else who has like a question right now that
yeah.
would like to share, or anything that needs clarification? Doesn't have to be a question, could be, hey, could you clarify this thing that I did not follow completely?
Yeah. This was one run through relatively quickly compared to the subject matter. So like definitely there's I can imagine those questions coming out. Yeah.
All right. And if you want me to take a look at your summaries before you submit them to get your points, happy to do it.
Yeah.
Philosophical walks are my thing. So most of you having my students, so you know how it works.
Right. Do you remember, Professor Barrantes, last time you spoke at Philosophy Club? We did it in person. There's no recording of that, but we talked about explanations in mathematics in a very general way. And one of your illustrations has kind of stuck with me, where you were using a parabolic equation to solve for a variable, and mathematically came out to a result that is like both positive and negative, because either would work in
Nice.
how math works. And I'm thinking, and as a very like simple analogy, a very simple illustration of like the concept of like the epistemic differences between humans and computers in this case. I would intuit that like a computer simulation is about one categorization or one computation off from reporting like negative momentum in a case like that, in a when it's fed an empirical situation that covers a parabola, and I wonder, as a way of like contributing as much as I can to like the formation of these arguments, or maybe just the conveyance of the arguments, including that illustration, just because it has at least stuck with me, might be useful, assuming that covers the right phenomenon. You know, if there's
Yeah,
a conceptual possibility that a computer could like spit out a negative number
nice.
erroneously like that, you know?
Yeah, yeah. So that example actually comes from this paper, I think, or Bueno wrote another paper the year after. I don't know which of the two papers, but I think it's from this paper. You know, the notion that you throw a rock in the air, then you calculate the time, and then you're going to have t squared equals 4, and you have to make a choice, right? What am I going to do with the -2, right? And what Bueno says is that, you know, yeah, you do your derivation, and then you need to interpret back the result, right? But you are mostly guided by what you know applies to the world, and that's it, really, right? You don't really need to understand why the -2 happened, right? Whereas in the case of a simulation, because sometimes you are in situations that you don't know really what's going on, you do need this explanation of the result, right? And for all you know, the computer might make an association relating the result to something that you could not, you know, you couldn't have foresaw beforehand, right? Now there is a point where you're gonna be like, yeah, but you know, is this category a real one or not? How can I verify? Do I have independent confirmation, right? But depending on how comfortable you are with removing yourself from the center of the epistemic enterprise, right? So that's why this is so interesting and yet complicated.
Yeah. Yeah. Would it be productive, do you think, to add that sort of framing into this overall, presentation?
Mm,
Because it feels like it's kind of like a separate but important point, right?
yeah,
That it could be either party at the epistemic center, uh,
yeah,
even though the example of a rounding error causing causing this kind of thing
uh-huh.
is relatively unequivocal.
Yeah,
Yeah.
yeah. Yeah, I mean, there is here's a limitation. I already mentioned that I'm not the expert on this side of the paper, so I'm using the example that I understand. But I know there are way more complicated examples, and you really need to get into the details of how the simulation model was constructed in order to explain what's going on, right? So, but this straightforward case helps me illustrate my point that you do need an explanation here, whereas you don't in the other case. But I'm sure there are models where whether or not the result corresponds to reality is not as straightforward as in this case.
Yeah. Oh, for
Yeah.
sure. Yeah. So it has been just over an hour.
Perfect.
Oh, we have never mind.
That's a
Clapping in the
clapping.
chat.
Right, Carissa. Hi, Carissa.
I meant a hands up. I was just gonna say because
Oh,
we kind of talked about some of this, and because I have philosophy of AI with McCormick and different like computer simulations, like trying to determine which way a pen will fall, or the AI will try to like recreate things, but usually like it may have fault because it'll create symmetry when it's asymmetric. So I think that kind of relates to like the simulation.
Yes, nice. That's a good example. That's definitely a good example, right? And if anything, all these examples show that there's a more basic point, which is you don't simply use the computer as a calculator, right? There's much more involved, right? And that's why the results cannot be straightforwardly interpreted back, right? There's an extra. I mean, in the case of mathematics, there is already an interpretation, right? But in the case of computer simulation, you have this extra layer of having this necessity of explaining what's going on. Otherwise, you're not going to have a starting point for your interpretation.
Am I right in inferring that if you have optimal representation that the explanation model doesn't pertain in those cases, or is the explanation like it's still is the explanation that it was optimal representation and that's why the simulation spits out the right result when it does?
Yeah.
Or something along those lines.
Yeah. So in the case, I mean, I introduced the notion of optimal representation as a way of dispelling the mystery surrounding mathematical explanations of physical phenomena. Yeah. Because really what's going on in these cases of mathematical explanations is that people thought that if science dictates ontology and mathematics is indispensable to explanation, and the way science dictates ontology is by inference to the best explanation, then they put, all these together and, if you believe in electrons, you have to believe in numbers, right? So basically, the mathematical explanation of physical phenomena literature was introduced or got like super excited because these cases were supposed to prove once and for all that mathematical entities exist, or that at any rate, that if you are a scientific realist who believes in an observable entity such as electrons and evolutionary processes, and you are not a mathematical realist, then you're a filthy hypocrite, right? And my view is that that argument doesn't follow, because ultimately, even in cases of mathematical explanations of physical phenomena, what you have is that mathematics is tracking down empirical structures, but people are misled by the highly mathematical nature of the physical phenomenon to be explained. And I use highly mathematical loosely, right? In an ontologically non-committal way, right? So this object here, which is physical, happens to be perfectly representable with a graph in a way such that, you can literally forget about the system and work only on the graph, right? The received view is that every time you implement a mathematical model, you need to introduce approximation, abstraction, idealization. You need to distort the target in order to fully represent it with math. But in these cases, it's straightforward, right? And that's why you have the impression that you're dealing with a mathematical object, but it's ultimately a representation. That's my main point, right? And that's why, I think that these examples don't support the view that there is a genuine mathematical entities doing explanation in science, and therefore electrons and numbers are on a pair, right?
Yeah. To possibly just rephrase that, but I don't know if it might be helpful. There are certain aspects of a situation of the empirical setup, or maybe in the derivation of an empirical setup that we just don't care about. So when you're looking at a system of bridges and islands, or a system of a pen and free fall, something along those lines, there are certain aspects of those situations that you just don't care about, or that aren't salient to the explanation you're ultimately trying to generate, the theory you're ultimately trying to come up with. I don't know, something like
nice.
How fast the pen twists when it's in the air is just not relevant. We don't care. How far the distance is between the bridges and the islands, we don't care. That's not to say that those things don't matter ever or at all. It's just that for the questions that we're all trying to answer, usually they don't matter. And that also suggests to me that, like, in order, there's a certain way in which the framework where mathematical explanations are paramount, or directly tied to ontology in the way that you illustrated earlier, because there's a certain way in which that view, that received notion, kind of dictates or distorts the kinds of questions we ask, the kinds of things we care about. Like there was a point at which someone decided that we're going to try and figure out if you can walk across all these bridges without retracing your steps? Kind of an arbitrary question, interesting, but not like, you know, a different model of how explanations work generally might have generated a different kind of question, you know?
Yeah.
So,
Yeah,
so
I mean,
I'm interested in that.
yeah, I mean, and you have the empirical, and I have like a very broad notion of empirical here, right? I'm just, you know, talking about something that is from the world and is not mathematical, right? So
Yeah.
it can perfectly include human intentions, etc.
I do love the phrase ontologically non-committal. That's like my new favorite. I think that's all I've got for like substantive questions and comments from me at least. Is there any other anybody who wants to contribute or comments in the chat or in the meeting room?
Well, thanks everyone, and thanks William for putting this together. It was a great opportunity, and thanks everyone for listening to this talk, and glad to see familiar names.
Yeah. I'm still sorry that it has taken me all semester to put even one of these meetings together. Daniel graduated is what happened.
It's nice. You're doing a great job. You're doing a great job. This is awesome.
All right. Well, I'll reiterate that. Thank you, everybody. And those of you who are watching this later on, thank you to you as well. This isn't like this is not going to be like, this is never going to be like a monetized project or anything, but we appreciate the views. And yeah, I think that's all I got. Look out for more Philosophy Club stuff if you're in the discourse or on the Canvas page, the Discord, or on the Canvas page. And when and if we arrange stuff in the future, you'll know about it. So thanks again to Professor Barrantes and everybody who's here. And I'm gonna hit the stop recording button. Good night. Drive safe.
Okay, bye.